Hi guys, so in today's video we are going to be talking about asymptotic bounding and what is the significance of asymptotic bounding in algorithms. So the three types of boundings that we're going to discuss in this video is going to be the upper bound, which is big O notation, the lower bound, which is the big omega, and the average bound, which is big theta. And in algorithms, we believe that big O denotes to the worst time complexity, big omega donates to the best case time complexity, and big theta donates to the average case time complexity of any function or any algorithm that we're trying to design. Now, how to basically solve big O, big omega, and big theta questions. So first of all, let's start with big O. So for big O, we say that our f of n, any function, should be lesser than equals to some constant c times g of n, where n should be always greater than equals to n naught. Okay, so basically what this means is that if I have some function f of n, then this is some n and this is some n naught. And based on some n naught, our function g, let's say this is our function g, when multiplied by some constant c, should always be greater. This function, this entire function should always be greater than f of n, starting from n naught till n. So usually we try to limit this n naught as 1, but there are some cases, some types of functions where we cannot limit this to 1, and sometimes this n naught has to be 2 or 3 or 5 or 10 or something like that. But we try to keep n naught as minimum as possible. Moreover, this n over here denotes to the number of instructions. So this is basically the number of instructions in an algorithm. So for example, um, if I have int x equals to 2, int, or if I do x plus plus, then I will have 2 instructions. And what that basically means is that that n can't be decimal, can't be decimal, and that n would always be an integer, right? So be wary that n will always be increasing in terms of increments of 1, 2, 3, 4, and there will never be some decimal values of n naught. Okay, so now that we know some basic intuition of what we have to do for upper bounds, let's try to solve a question. So the first question that we're going to be solving is going to be for 6n plus 3. So for a function f of n defined as 6n plus 3. And we are going to say that, let's say that 6n plus 3 is going to be lesser than equals to, let's say, 9n. Okay, let's take 9n for a second. And I'm going to demonstrate this by using a website called Desmos. This is a very nice website for showing graphs. If you want to use it, you can use it on your own as well. So I highly recommend you to go on Desmos and to do these things by yourself as well. So the first function, that our function is f of n, is defined as 6x plus 3, which is denoted by this red line. Okay, and the test function that we are saying is always going to be greater than f of n is going to be 9x. So let's try to see if that works out for us or not. So I'm going to write 9x. Okay, now to make things simpler, let's just give this some intercept. So 1 comma 9. Let's label that point. Okay, so we can see that, now remember, the red line is donating our f of n, and the green line is donating the g of n, c times g of n. We can see that after the value of 1, after the value of n, basically this the x is basically the x-axis, the n. So after 1, your function of c times c of n will always be greater. It will always be greater than your original function. And the way how you do these questions is technically is because the way how you do this is you try to see the highest one strategy on how you do these types of questions. You try to see the highest class function, which I'm going to go in a little while as to what are class functions. But the class function in this is n, and we try to make every single constant or anything, any constant as that class functions. For example, if this was 6n, we also made this 3 as 3n, and that basically gave you 9n. For example, if I had some other question, um, if I had 5n squared plus 6n plus 3 sometimes c times g of n, then we would do something like 5n squared plus 6n squared plus 3n squared, and that will always give you some c times g of n function, which is always going to be greater than equals to f of n. So that is a very nice strategy that you could use. However, some can argue that, let's say, instead of taking 9x, I could have taken 50x. That would always work. Some would say, okay, I didn't take 9x, I took 25x, or let's say 10x or 15x. And as you can see, in either of those cases, your function is basically greater than your f of n, and that basically checks out. As long as your function is greater than your um, your asymptotic bound, uh, as long as this function is greater than your original function, it works out. Um, and that way we can say that we might have different answers for basically this will have different answers, right? Someone could say, okay, 9, and someone would say 15, and someone would say 20, and so on and so forth. So to avoid that confusion, when we are taking the big O notation, we often try to ignore the constant. So the big O notation of this would just be n. And we say that the worst time complexity of this is just O of n. Okay, now let's talk about class functions for a little while. There are some types of class functions, so I'm just going to list them down over here. We have O of 1, which is always lesser than O of log of n, O of root n, then we have O of n, then we have O of n log n, then we have O of n squared, then we have O of 2 n to the power k, then we have O of 2n, then we have O of n to the power n, and then we have O to the power 2 to the power 2n. So these are some class functions that we have decided that the time complexity of big O's is going to be represented in this order, and we are going to find out why this is the case. Okay, so we were discussing about O of n, right? Let's try to take something lesser than this. Let's take O of log n for a second. If we take O of log n, if we take O of log n, right, we can see that this is not an upper bound. This c times c, this function is not an upper bound for our original function, so this does not qualify as big O. Okay, well, some might argue, let's try to increase the value. Okay, let's do like 10. Okay, 10 doesn't work out. Okay, 100, let's try 100. Oh, 100 is working out. Wow. So does that mean that this is an upper bound function to 6x plus 3? No. Why not? Let's try to look at the bigger picture. And at the bigger picture, you can see that at x equals to at x equals to 1, this was getting satisfied, but at n being 1, around something around 120 or something like that, this statement went false, and we said that this should work for all values of n. It should work starting with n naught, which can be something like 1 2 10, something like that, but it should always work till all values of n, which means that this estimate is not good. And that's the reason why we say that the big O notation, that O of n, this linear line will act as an upper bound for log of n. So that's the reason why we have placed log of n over there. Let's try to see what is the case for O of n squared. Okay, so let's take x squared. Okay, if we take x squared, we can see that, okay, where's my intercept? There's my intercept. Let's zoom in on my intercept. Okay, so at my intercept, we can see that my linear function is still acting better than my quadratic function, and we can like improve our quadratic function by like saying 9x squared. Yeah, now it's better. Now at x equals to 1, both our function and basically our test function g of n, c times g of n, is at 1. But as the value of n increases, we can see that indeed your x squared is always, always, always on the upper side of this f of n, or your linear function, which is 6x plus 3. So that is basically the concept of class functions. And technically, when I said we're basically looking at the worst case, right? The worst case in terms of big O notations, and that's the reason why I said that whenever you're looking to solve these types of questions, you have to look at the highest class function. So for in this case, the highest class function was n squared. It wasn't n, it was n squared. That's why we decided to like add or multiply n squared to all of these terms and then add them together. And like I said, you can have multiple answers. For example, some might say 100 n squared, some might say 1000 n squared, and that also works out. And you're at the end of the day, you're just going to take the big O of that thing, and that's just going to give you O of n squared, which is really important. Now that we've discussed a basic intuition of what asymptotic bounding is, some might argue that, okay, so you're saying that you can take any big O notation. You could have taken O of n, you could have taken O of n log n, you could have taken O of n squared, you could have taken any of those functions, and that all of those functions would act as an upper bound for function f of n. Yeah, you could. However, whenever we're trying to solve questions like these, we always try to take the tightest bound. So we always try to get as close to our function f of n. And that's the reason why we would prefer taking O of n rather than taking O of n squared instead. So always try to take the tightest bound, which is going to be f of n. In this case, it would just be a linear. It would just be a linear function itself. And that is basically how you solve big O notations. Now, the concept of big theta is just the opposite of big O, and basically big theta just says that f of n is going to be greater than equals to some c constant times g of n for n not greater than equals to n. And what we can basically say about this is that if we say this chart is very important, because if you look at in this way, you say that all of these functions that I just highlighted are always going to act as big O notation for O of n, right? Even though we prefer O of n because that's the Tyler-Disk bound, but these all of the functions act as um, as an upper bound for O of n. And we could also say that these functions will always act as a lower bound. So technically, I can say 6n plus 3 is always going to be greater than equals to n. Is that the case? That is the case. And that is acting as a lower bound, as the lower bound of f of n. Some would say, okay, let's take log of x. And that too would act as a lower bound of this. But since we are always looking at the tightest bound, therefore we would prefer O of n rather than these other functions. My last thought on this topic is going to be for big theta. And big theta is just going to be f of n, where you have c times some c1 constant times g of n and some c2 times function g of n. And observe that the function g of n is same in both the right side and the left side, which means that whichever class function that you are choosing for f of n, g of n should be same for both the lower bound and for the higher bound. And for f of n, we can see that if we have O of n, which is if we have n over here, and if we have g of n as 9n, this n is basically the same class function, even though, yeah, it is the same class function, which is basically n. So that is big theta, and that acts as the average. And you can see that if you take the average of O of n, the big O, if you take the big O notation, if you take the average of this and the average of this, you should get an average of theta n. So that was all about asymptotic bounding, and I hope that you have now gotten a better grasp and understanding of the concept of asymptotic bounding. So yeah, thanks for watching.